Hi, and welcome to another video where I'm going to be implementing what we are starting to call a geometry gem, which is basically a super simple algorithm to do some kind of geometry analysis or manipulation. Today's video is going to be about calculating the distance between a point and a line. And the interesting thing about this problem is that that point, that distance that can be thought as a line that is perpendicular to the first line that we're analyzing. And in order to do this, we're going to apply a lot of we're going to learn a lot of vector algebra. So like you can see here, so you can see that what I have here is a point that I can move around in three-dimensional space, and then I have a grasshopper definition that is giving me the distance of that point to that line that I just formed. And what we're going to implement is these two very interesting functions on how to analyze this problem with vector algebra. And what I'm going to do is I'm going to explain how we can think of this problem as, instead of 3 points, so the point that we want to project and the two forming the line, we can think of this problem as two vectors. So the vector that defines the line and the vector that defines the starting point and the point that we want to analyze, and how through some vector algebra we can find the straight distance between P and the line formed between A and B. We're going to do this in two different ways. First, the one that you see here, which is we're going to apply a little bit of trigonometry, and we're going to use the properties of the dot product of two vectors. And then the other one that you're seeing on the other corner, which is going to not use trigonometry at all, but take advantage of a really, really cool property of the cross product of two vectors. Okay, so if you're interested in this, follow me and let's get coding. Great, so let's first start with the basics. What I've done here already is I have created a simple grasshopper definition that takes 3 points that are coming in from Rhino. So this point here, the point that we want to calculate the distance to the line, and then 2 points that are going to define the line that we want to use for calculations. So I've created like a very simple vanilla definition where I'm creating a line between those 2 points, and then I'm finding which one is the closest point to this one on the line, which is also the one that ends up being perpendicular to this line. And this component gives me the point, it gives me the parameter, but it also gives me the distance between the projected point and the point on the line, which is the value that I want to calculate with this geometry gem. Okay, so I'm doing this just for the sake of verification, to know that my values are correct. So I have created a C# script component here that takes P, the point that I want to verify, and then A and B, the 2 points that form the line that I'm going to be projecting on. So I'm going to plug those 2 in here, and as usual, you have to remember to right click on the input and specify the correct type. So these are going to be point 3D, each one of them point 3D and point 3D. And then here I'm going to plug in a panel to make sure that we understand that we get the output. And with this, I'm probably ready to start coding. But as usual, and this is super, super important, I want to always invite you to take some time to think about what you're doing before getting into the code. So what I would like to do is I would like to spend some time diagramming and explaining what the algorithm that we're going to implement, how it works and where is that coming from, and to understand a little bit of the vector algebra that is behind what we're going to just do right now. So let's go into the whiteboard and let's break this problem down. So you can see here on the screen, I've drawn like the worst sketch ever to depict the idea of what we want to do. But the idea is basically this. We have a point P, and we want to find the distance h of that point P to a line that is formed between point A and point B. And it just so happens that the closest distance to that line also happens to be the one that is perpendicular to this line. So the line H is perpendicular to A and B. So why is this important? It is important because it helps us break down the problem through some trigonometry, and it also helps us because we can apply some of the interesting rules of vector algebra in order to figure out this problem. We have started this problem by talking about 3 points, but actually what I would like you to understand is that these points, these 3 points, are just 3 points floating in space. They don't have any known relation between them, but we're actually going to assimilate these 3 points to two vectors, and using those two vectors, we will be able to operate and find the distance h that we're trying to find here. And those vectors are going to be, first is going to be vector AB, a vector between point A and point B, so this point here, a vector that is basically representing the line that we are, that is formed between point A and B, and then another one, another vector that is going to be between the starting point of the line and point P. Actually, it wouldn't matter if we used the vector between B and P. It doesn't really matter, but we're going to operate between those two vectors so that we can find the length of the distance between P and this particular vector between A and B. Today, in this stream, I'm going to show you how to calculate that distance in two different ways. And the first one is going to be using the properties of the dot product of two vectors. Why are we doing this? Because if you think of these two vectors in three-dimensional space, you can see that because h is the length, is the segment that joins P and the vector A and B in a perpendicular way, it just so turns out that we can think of this problem as a trigonometry problem where we have a square triangle here. This here is going to be the length of the vector AP, so it's going to be how long this vector is. This h here is going to be the distance that we're trying to find, which we don't know. And then L is going to be this distance here between the beginning of the vector. This vector ends whatever, it doesn't matter. But L is going to be the distance between the starting point of the vector and where the segment h hits this vector. This is what is usually referred to as the projection. If we thought of this as a vector here, we could think of this as the projection of the vector AP on top of the projector of the vector AB. So this could be the projection of AP over the vector AB. So this is A, this is P, and this is B. And the angle that these two vectors form is called theta. We're going to call it theta, for example. What's interesting about this is that we can find trigonometry relationships between this this triangle. We will do that for the other way of calculating. But for here, the first one we're going to do is we're going to use the properties of the dot product. And if you remember, I may link to a video somewhere here that describes that. So if you remember, the basic rules of trigonometry say that the cosine of this angle theta is going to be equal to L, so that length of the projected vector that we don't really know yet, divided by this other side, the length of the vector AP, which we do know because we do know all those points. If we reshuffle this a little bit, we can see that L is going to be equal to the length of the vector AP times the cosine of theta. Okay? Now, where things get interesting is that we can manipulate this a little bit more and say, well, if this is true, then I can take this part and I can multiply both the numerator and the denominator by the same value. So I'm going to create a fraction here, and I'm going to say AP, the length of AP, times the cosine of theta times this new factor that I'm going to introduce, which is going to be the length of AB. Okay? And I'm going to also divide everything by the length of the vector AB. Why am I doing this? If I take something and I multiply it and I divide it by the same number, the value stays the same. Okay? So this that I just did here is exactly the same as this that I just did here. But why am I doing this? Because if you remember from vector algebra, and I will point to some documentation here on the videos, this that I have here, this part, equals the dot product of two vectors. So if you remember, if I have vector u and I have vector v, the dot product of those two vectors equals the length of one, the length of u, times the length of v times the cosine of the angle that they both form. Is one of the properties of the dot product. So what is interesting about this? What's interesting is that now this length here is going to be equal to the dot product of u times v divided by, oh sorry, it's going to be equal to the length of AP times the length of AB. No, sorry, I'm messing it up again. It's going to be equal to the vector AP dot product, the vector AV, divided by the length of the vector AB. Okay? And if we push this a bit more, if the length of the vector AB happens to be 1, if we unitize that vector, then this is equal to the vector AP dot product, and I'm going to put a hat here. The hat means that this vector has been unitized, okay? So this is AB, the unitized version of AB. Oh, right, so this equals the length of that projection here. Great, so as we just saw, I just wrote it a bit cleaner all the way up here. So we can, through vector algebra, we know that the length of the projection of the vector AP over the vector AB equals the dot product of the vector AP times the vector AB unitized, okay? The unit vector AB. But why is this important? It is important because now if we know the length of the vector AP, because it's just a given, and if we know the length of L, then we have a square triangle in space that we can apply the Pythagoras theorem to. I never know how to pronounce Pythagoras in English, but very simply, we can say that the hypotenuse, so the length of AP squared, equals the height squared plus that length that we just calculated square. Okay? And then the problem is just, I'm going to touch here, and then the problem is just as simple as we know this, we know the L, and then the problem is just as simple as figuring out H. So we can do here, we can do H is going to be equal to the square root of the length of AP squared minus L squared, which happens to be, as we just said, the square root of the length of the vector AP squared minus the dot product of the vector AP times the vector AB unitized, okay? And this is a square. So this very simple calculation is going to give us then the length of H, which is that distance that we wanted to find between P and the straight line formed between the points A and B. Let me write this in a clearer way, and I'm going to write it here, and then we get back to actually writing this in code form. Yes, so this is it. I just cleaned up a little bit, but remember what we just discussed, the distance H is going to be equal to the square root of the length of the vector AP squared minus the dot product of the vector AP times the unit vector AB, all of that square as well. As you can see, it took quite some time to break this down, but I really like breaking down these like small trigonometry problems, because now you can see that you now understand where this expression came from, and you will see how implementing that in C# is going to be a piece of cake. So let's go ahead and do that. So I'm going to go back here to my script, and then I'm going to take here, I'm going to open my script, and I'm going to say, well, I'm going to write, first of all, according to the algorithm, what I want to do is I want to create the two vectors, AB and AP. Okay, so AB is going to be the vector formed by subtracting the coordinates of point B minus the coordinates of point A. And then the vector AP is going to be the same thing, subtracting the coordinates of point P from the coordinates of point A. Is that working? Yes, it's working. And something that we may want to do is going to be, well, let's first calculate the value of L. So if you remember, let's first calculate the value of L, which I'm going to name the cross product, because this is going to be equal to the cross product of two vectors. One is going to be AP, and then is going to be the unitized version of AB. Let me do that as well. I want to say AB dot unitize, or we could do this manually, but we're just going to use Rhino Commons methods for that. But unitizing a vector is just as simple as dividing that vector by the length of that vector, just so that you guys remember. And then the cross product of these two are going to be AB times, which is already unitized, so AP times AB, which is already unitized. This cross product is going to be the length of the projection of AP over AB. Okay, and now going back to the only thing that we need to do to calculate the height is going to be the square root of these values. So I'm going to write here, I'm going to write double H is going to be math dot square root of what? It's going to be the length of AP, and we may want to calculate that as well. Length of AP is going to be equal to AP dot length. Okay, and then here we just say the square of that. So length AP times length AP minus the cross product, the square of the cross product. Is that correct? So you see here the square root of the length of AP squared, so AP times AP, and then minus the cross product of AP times the unit vector AB squared. So as we just saw, this is cross, and then let's see if that works. I'm going to output there, and boom, it works. We have the, we can move these points around, and then we have the straight distance between point P and the line formed between vectors, between the 2 points A and B. Okay? And we did that with very simple vector algebra, only doing some trigonometry and understanding the relationships between those two vectors and their square triangle in space. And also with a little bit of the aid of the dot product properties. Okay? So let me take a little bit of time to take this code that we just wrote, and instead of having it as part of the main code, just write a very clean function that takes these three vectors, these 3 points, and then gives you the result. Okay, let me rewrite this in a second. Voila! So we have it here. So you can see that now my code is a little cleaner. I have packed this functionality that I just created into a function called distance to line, and I wrote dot product just because I'm going to do a different version of this. So I want to make sure that I know which version I'm using. This function takes 3 points, P, A, and B, and then returns the distance between that straight projection of P over the line of AB. And then I can just use this function now to calculate this. And the nice thing about this is that this function now is a self-contained function. So I could just copy paste this between this implementation that I wrote here in C# in Grasshopper, and then with very minimal changes, I could just implement this in like a pure C#, in like a pure C# script, in like a pure C# program, a library, other environments that use C#, like Unity, like VVVVV, like you know, all those things. So I think this is great. So I'm going to keep this here. And then what I'm going to do now is we're going to move to using a slightly different approach to calculating the same distance. But instead of the dot product, we're going to use now the cross product, which is definitely my favorite. Okay? So let's do that. All right, great. So I have created a new diagram because what I would like to explain now is an alternative method to computing this distance h. And instead of doing so much trigonometry now, what I'm going to do is I'm going to use one of the nicest properties of the cross product, which is the fact that the cross product equals, the length of the cross product equals the area of the parallelogram formed by two vectors. Let me explain what that means. So if you remember, the cross product is the multiplication of two vectors, but as opposed to the dot product, which gives you a scalar, it gives you a number, the result of the cross product gives you another, the result of the cross product of two vectors gives you another vector, which happens to be, first, one of the first properties is that it's perpendicular to the plane that those two vectors form. So those two vectors always form a plane. So the cross product is perpendicular to that plane and with the orientation defined by the right-hand rule. So if I multiply AB cross AP, then you guys no, this is mirrored. This is, sorry, the camera. This is mirrored, but it will be pointing in this way. So this would be the right-hand orientation of this cross product. All right, but most interestingly, what happens is that the length of this vector, the length of the cross product, is equal, and I'm going to make another diagram next to it, is equal to the following. So if we have these two vectors here, those two vectors in the plane that they form a parallelogram like this. And it just so happens that the length of the cross product equals the area of this parallelogram formed by the two vectors. And why is that interesting? It is interesting because we can also use the formula of how to calculate the area of a parallelogram to then find the height. Let me show you that. So if you remember, and you can Google this, the area of a parallelogram equals the base of that parallelogram times the height of that parallelogram. The base would be this one, so it would be B, and the height would be this one here, which, as you can see, this is exactly, H is exactly what if I draw this parallelogram here, you can see that that H is exactly the value that we're trying to find, right? Which means that here the value of H equals the area of that parallelogram divided by the base of the parallelogram. And guess what? If we transform this A and this B in vector parameters, what just happens is that what we get is that B, the length of the base, equals the length of the vector AB that we have here. So the length of the vector AB, right? And what is area? Area is equal to the length, as we just described, is the length of the dot product. So it's equal to the length of the vector AB cross product. It's usually used this cross product the vector AP, the length of that cross product. And literally, that's just it. So let me rewrite this in a way that it looks a little bit better for the sake of the diagram. Give me a second. Exactly. And this is what I wanted to get to. So as you can see now, finding the value of H, that distance, is just as easy as computing the cross product of vector AB and AP, and remember that the order is important in this one, computing the length of that resulting vector, so those are the two vertical bars that you can see there, and then divide the value of that length, which is the area of the parallelogram, by the length of the base of that parallelogram, which is literally is just the length of the vector AB, which is that's what we're representing with those two vertical bars. All right, so I mean, how easy is this then? Let's now Let's now go back to the code and then to implement this. So I'm going to do it right away now, just because I want to be clean. I'm just going to do this right away on a function. So I'm going to write a function here called dist to line, but now it's going to be cross product. And I'm going to take the exact same inputs. Then I'm going to calculate vector AB. I'm going to remember copy pasting is the devil, okay? You've seen me have a lot of problems before doing this, but so be super careful whenever you copy paste code, okay? And now we have the vector AB, we have the vector AP. We can calculate the cross product. So vector 3D cross product equals, and we can use, for example, the static function in Rhino Common. For example, AB and AP. And if you guys are interested in how to actually perform the cross product, there's a lot of documentation out there. I can point to some videos here on somewhere. Otherwise, maybe we can actually do this. If we have like a few minutes, we can extend this and just do this manually. That might be a good idea. And then I have the cross product. I have so for example, I can calculate the length of the cross product is going to be equal to cross dot length, just as simple as that. And then what else? If you remember I have to calculate the length of AB. So let's do that. Double A length length AB. I'm just being very verbose and writing a lot of variables and stepwise so that you guys can see. But this could be written in like one line of code. It's just not so easy to read. And I like code that is easy to read and understand, even if it's not so performative, at least for education. And then now that we have both lengths, then the height is just as easy as dividing the length of the cross product by the length of the other vector. So double H equals the length of the cross product divided by the length of AB. And let's return this. Let me see if this works. First, are there any errors? Nope, I didn't have any errors or typos. And then what I'm going to do is I'm going to reshape these outputs, and then this is going to be distance by the dot product, and the other one is going to be distance by the cross product. I'm going to plug them both in here, and d dot is going to be equal to the function that we used before, but now d cross is going to be equal to this to line, but cross product, and then P, the point P, point A, and point B. And let's see, da-da-da-da-da-da-da, boom, it works. Oh yeah, I love vector algebra. It's one of the coolest things in the world. All right, let me recap. I'm gonna go back to the diagram. So what we just saw here is, I'm going to turn on both diagrams. What we just saw here is two different approaches to calculating this height here. So I'm going to close this. Two different approaches to calculating the distance h between a point and two lines AB. And a line and between the distance h between a point P and the line formed by 2 points A and B. In one, we were using the properties of the dot product and a little bit of trigonometry. And then on the other one, we were using the properties of the cross product of two vectors and literally not trigonometry whatsoever. So from a performance standpoint, they're both very similar, I think. So it doesn't really matter which one you use too much, unless you're doing this like a million times. So just choose whichever you find more useful, more easy to understand, or more practical to implement in whichever framework you're using, okay? And I think with that, I may want to wrap it up. No, what I'm going to do is like bonus points. I'm going to actually write two functions to calculate the dot product and the cross product of two vectors, just for the sake of it, just because I like this a lot, okay? But if you're not interested, if you know how to do that, then this is the end of the video. So see you on the next geometry gem. Yay, let's get to this. Let's do first, I'm going to do the cross product, the dot product. Dot product between two vectors, so vector 3, I'm going to call this U, and vector vector 3D.v. And if you remember, the dot product first is a number, so we're going to return a double. And second, it's very easy to compute. So actually double dot is going to be equal to the sum of the multiplication of the components of each one of the vectors. So this would be u dot x times v dot x, then plus u dot y times v dot y, plus u dot z times v dot z. And we just return that. And actually, if we want to really shortcut this, we can just return that value right away. Okay? So let's see if this works. Let's substitute this function with whatever we have used the dot product first. So the dot product here. So the dot product of AP and AB. And then have we used that anywhere else? No. So I'm going to run this, and yes, the result is the same. So yep, pat in the back. I know my dot products. The one that I never remember and the formulation for is the cross product, so I had to look it up. But you can see here the dot product is the result of, is the determinant of multiplying two vectors by an ijk unit unit vector. So, but you can see here that the first scalar component of the vector is the second scalar component by the third minus the third and second. So let me just put this here on the side. I cannot have. So I'm just gonna put it here on my other monitor here. So first, remember the result of the cross product is a vector object. So I'm going to create a function that returns a vector 3D, and I'm going to call this cross product. And this is going to take two vectors and its inputs. So here, so I'm going to calculate first the x coordinate, and this, as I said, this is going to be equal to y of the first vector times z of the second vector minus z of the first vector times y of the second vector. So let me write that down here. So that's going to be u dot y times v dot z minus u dot z times v dot y. It's very important that you do this super carefully, because if you mess this up, and it's very easy to confuse z, y, v, blah, blah, blah. If you mess this up, it's really hard to debug and find. So I'm going to be super, super careful by doing this. So y is going to be equal to u times z times v dot x, right? Yes. Minus u dot x times v dot z. And you can see that there's like a little bit of like a logic here of how things flip, right? This is lowercase, and then double z is going to be equal to u dot, probably is going to be x, right? U dot x times v dot y minus u dot y times v dot x. And I also got a typo here, u, and then I can just return a new vector 3D that has these components that I just calculated. Okay, this doesn't give me any error, and I'm going to now substitute this where I have cross products. So here with my function, my own cross product implementation, and if I multiply this, there you go. And actually, I just noticed that I have like a huge confusing thing. This is not the cross product, this is the dot product. So that was not great. I'm just going to replace this here. I'm sorry, I made that, that was confusing, okay? That should not have been there. But I think that's it. So with this, now we have our function that calculates both the distance using the dot product and the cross product. And we also have like a bunch of utility functions that give us like a lot of goodness. So I think with this, we're ready to go. With this geometry gem, I hope you liked it. I hope you learned some trigonometry and some vector algebra. This is so cool. And just a reminder, I wanted to build these two gems today because I would like to use this functionality, calculating the distance of a point to a line, to a straight segment line, for a next gem that I'm going to record in a second, which is going to be the Douglas-Pecker polyline simplification algorithm, which uses this. Okay, so if you're interested in that, I will probably have like a link to that video popping up somewhere here, or just like I'll just like go through the description and you will find that. Okay, well, thanks a lot for sticking around.